Okay, so in the last class we were talking about this general problem called the marginalize a product function. So we are given quantity of the following form, summation over all to x n alpha 1 of 1 alpha 2 alpha m of x m, where each alpha I is a function of some subset of the variables. There are a total of n variables, right? Each variable coming from some alphabet xi from alphabet ai, and the goal is to compute some function of this particular, either this particular form, or you may want to compute x some sj element beta of x j. So I want to marginalize this particular function. So this global function is a product of m local functions, and the goal is to marginalize the global function with respect to some subset of variables. So the naive way, of course, you can always do it in a naive way. This requires a number of operations which grows as the product of a1 am, right? So certainly with these many operations, this times probably the number of functions m times this. So in these many operations, it's possible to compute this function. Question is, can we do better? So it turns out that in some cases we can do better, some cases we can't. So we want a principled approach to compute this quantity as efficiently as possible. When it is possible, we do it as efficiently. If not, well, you can't do any worse than this anyhow, right? And in the previous class, we saw a bunch of different examples, all of which could be stated in the framework of this MPF problem. We looked at decoding linear codes, computing the Hadamard transform. You can also compute the Fourier transform, decoding linear codes, both again depending on which semi-ring you choose. You can get either ML decoding, ML symbol-wise decoding, or ML block-wise decoding, and even statistical inference problems for Bayesian networks, and even decoding convolutional code. So all of these and many more can be set in the framework of this MPF problem. If we have an efficient way of solving the MPF problem or a general semi-ring, then we have a method of solving any of these problems. Right? So let us see how we can possibly do this. So in order to solve this, we'll use a sort of a graphical approach. So we have a bunch of quantities. So this is, you can think of this as an analytic approach where you try to sort of compute this, right? So one way of using, if possible, you could use the distributive law to write this sum of products as maybe some product of sums. Somehow use the GDL and then use the distributive law, try to get some terms together. So for example, in the toy example that we had, f of xy times g of yz, you could instead of summing over everything, there was a way to write the sum of products as a sum of product of sums. You could possibly marginalize with respect to some variables, right? But to do this in a more systematic fashion, we'll use different graphical approaches. no one way to do it, and really designing the graph is in many cases more of an art than a systematic. But in some cases, we know the ways to develop this graphical approach in a very efficient. But as we'll see, once we have a particular graph which describes the, the, the MPF problem in a systematic way, then onwards the algorithm is fixed. But as it turns out, in many cases, the designing of these particular graphs that requires a little bit of intelligent design. Sometimes it's pure luck. So we'll see some graphical approaches or graphical representations of a given MPF problem. Right? So I'll introduce two different graphical representations. One which is sort of fully systematic, but may work, may not work. There'll be another approach where we can solve the MPF problem exactly. But both of them will be important. We'll see each of them in a certain level of detail. Particularly when we go to LDPC codes, design a good decoding algorithm for LDPC codes, one of these will be used. So the first graphical representation is what is called a factor graph. Right? So the factor graph is the following. Remember that we have m local functions and n variables. So a factor graph for this, or one particular factor graph for such a problem, is to draw a particular bipartite graph. So bipartite graph consists of a bunch of vertices on one side, left side, and a bunch of other vertices on the right side. And there are edges only between vertices, only edges go from left to right, but there are no edges among vertices, between vertices on left side or on the right hand side. So the factor graph for any such product function can be drawn in the following way. So you have n left vertices, one corresponding to each variable. Okay. And you draw m right vertices, one corresponding to each local function. Right. And you draw an edge from the ith left vertex to the jth right vertex if the ith left vertex participates in the jth local. So if alpha 1 is a function of maybe x1 and x2, then there are edges from x1 to alpha 1 and x2 to alpha 1 and no edge from the rest to alpha 1. Similarly, if let's say alpha 2 is a function of xn and x1, then there are two edges incident on alpha 2, one from x1 and the other from x, and so on. Right? So there are always edges from left to right, but no two vertices on the left hand side are neighbors, and no two vertices on the right hand side are neighbors of each other. So this is one particular graphical representation, and this is the graphical representation that will be most used when we deal with LDPC in particular. So let's take maybe one or two examples. So we'd always work with this toy example that we had, so which was f of xy, g of yz. So this has three variables, x, y, and z, and two local functions, f and g. So f is a function of x and y, and g is a function of y and z. So this would be the factor graph. It would be one factor graph corresponding to this. That for the same function, it's in fact possible to draw different factor graphs. You introduce new variables or you sort of merge variables and so on. There are more sophisticated ways to draw this, but this is sort of the simplest way to construct the factor graph for any function which can be represented as a product of local functions. So let's take another example of maybe an LDPC code or any linear code for that matter. Again, remember that the form of the code that we're most interested in is basically the parity check representation of the code, because those are the constraints that you have on each code. So remember that when you're trying to do ML decoding, recall that the ML estimate is you perform some kind of a max, but the actual global function is this particular quantity, or this is a better version, in this particular quantity, right? So you have n local functions corresponding to each xi yi pair, and n minus k other local functions, one each corresponding to a parity check. So let me just copy this. See? This is our global function. Right? So how many variables do we have? Two n variables. Right? Each, so you have x1 through xn and y1 through y. Okay. How many functions, local functions, do we have? How many? 2n minus k? N minus k? Okay, what about these? So n minus k plus n, which is 2n minus k. So let's write down all the variables. First write y2 up to yn, x1, and you have local functions, one corresponding to each y1 given x1, 2 given x2, and so on. Yn given xn, and you have local functions, one corresponding to each parity check. So for each of these local functions, the function of y1, second is of 2, and these really depend on the code itself. For example, if x1, x2, x3 participate in the first parity check, do something like this. Right? So maybe let's take a specific example. Let us take h to be 2. Let's maybe take this. So it's the block length is 5. So there are a total of 10 variable nodes, one through x5 and y1 through y5. y1 1, y2 given 2, y3 3, and py x5. And we have two parity checks, one and this one, and corresponding to each we have an indicator function. First check, and this is the second. And the first parity check involves x1, x3, and x4. One, 3, and x4. And the second parity check involves x2 and x4. So this would be the factor graph corresponding to this particular linear. So in general, if you have a function with m local functions and n variables, then there are exactly n plus m vertices. This is one particular representation, and this is indeed the representation that we will use when we are trying to decode LDPC. But for the moment, we'll look at another representation, a graphical representation, one which is called a junction tree. So the junction tree, once again, is again, so the first case we had for factor graph, we saw that it was a bipartite graph, one represent. The junction tree is another representation, except that now the vertices and edges mean something different, right? So the junction tree, each vertex corresponds to one of the local functions, but we don't have separate we don't have any separate or vertices corresponding to the variables. Junction tree is, as the name suggests, it's a tree, and secondly, each vertex corresponds to a local function. or the corresponding local domain. Right? But this tree has to satisfy one particular property. If you look at the subgraph of all local domains or local functions, that involve any particular variable for every xi, if you look at the subgraph of all local functions which contain only xi, so you just delete all the functions which don't contain xi, this has to be connected. Okay, so let's just to understand, let's look at some. Again, we'll start with our toy example, f of x y times g of y. So you have two functions, or sorry, two vertices. One corresponds to of xy, the other corresponds to g of z. So if I draw an edge between these two, then is it a valid junction tree? It is. So if I look at just, okay, let's look at each of these. There are three variables, x, y, and z. Right? So look at the subgraph of all local functions which contain only x. That just has one vertex connected by definition. Now let's look at the second variable. The second variable is y. Look at the subgraph containing only local functions involving y, which is both. These two f and g are both connected. Look at z, the subgraph containing only of functions containing z is just g of y. Correct. Right? So it's a valid junction tree. Okay. Let's look at one of the examples that we had maybe over here. Okay. Let's take another example. Say beta of four. This is alpha 1 of x1, x2, alpha 2 of x3, alpha 3 of x4, alpha x1, x. Okay. So this should have four vertices. X3, 4, x4. So let's see if we can construct a junction tree with this. So let's look at the first variable, which is x1. Right? So the subgraph corresponding to functions which contain x1 should be connected. Which are those two? Which are the vertices? The first and the fourth, right? So alpha 1 and alpha 4 should be connected. So let's try to just draw an edge. Now let's look at x2. X. So which are the variables which contain x2? Alpha 1 and alpha 2. So let me draw an edge just to make sure that these are. Now x3 and x. So let's look at x3. It is alpha 1 and alpha 3. Let me draw an edge. x4 is alpha 4 and alpha 3. These two have to be connected. But now I run into a problem because this is not a tree. It has to be a tree. So certainly this doesn't give me a junction tree. Now, suppose this is a tree, but this is not a junction tree, right? Because if you look at the subgraph of all local functions which contain x3, that has alpha 2 and alpha 3, and they are not connected. So this is not a valid junction. We'll see that later. In fact, it turns out that you can't. You can't. But it is possible to construct a junction tree for this local function by adding some dummy function. So that is why for certain functions, certain global functions, you cannot construct a junction tree. But by multiplying some other dummy variables, in many cases, I mean almost always, you can construct a junction tree. But of course, that will involve more functions, and therefore more vertices than the original number of functions. So in fact, maybe let's look at this particular example. How we can sort of construct a junction tree for this function. So next. So to this, I'll multiply two more local functions, both which are identity. So I'll multiply with this with 5 of the x1, x2, x4, alpha 5 of x2, x3, x4. Alpha 5 and alpha 6 are always equal to 1. Okay. Any questions? Fine. So now with this, can we construct a junction tree? all of them are going to be connected to alpha. So can you just tell me? Let's take 2, 3, 4 alphas. You're saying all of them are going to be connected to alpha. All of them are going to be connected to that tree. How do you define a tree? Okay, what's another way to characterize a tree? Correct. So you don't have cycle. But if I construct, I take this. Does this contain a cycle? Start with alpha 4, go to alpha 6, go to alpha 5, and then come back to alpha. This contains a cycle. It's not a tree. Sorry? Okay. Four, 5 and alpha. Did you say alpha 1, 5 and 2, 3, 4 are connected to? Does it contain a cycle? Alpha 2, alpha 4, alpha 5 contains a cycle. Let's try this. So we'll see. So first we'll try to do it using brute force. I try to guess the junction. Right? 1, 2. Let me just write down the variables also. 1, x2, x3, 4, x1, 5 of 1, 6. So let me draw an edge between alpha 5 and alpha 6. Okay. From alpha 5, let me connect a 1 and connect. Okay. Firstly, there are no cycles, right? So it's a tree. That is fine. Now let us look at the subgraph corresponding to each variable. Let's take x1. So which functions do we have? 1, 5, alpha 4. So I'm giving you a graph. Giving you a graph. We want to verify whether this is a junction tree or not. So alpha 1, alpha 5 and alpha 4 are so the subgraph is basically this, just this. It's corrected, so that is fine. Now let us look at x2. Alpha 1 contains x2, 2 contains x2, these contain x2, this contains. So the subgraph is it is connected. Okay. X3, alpha 2, 3 of these two, this connected. X4, 4, alpha 3, alpha 5 and alpha 6. Connected. Okay, so this is a valid junction tree for this particular. No, not at all. So you just need a tree. So again, that is why it's important to see what properties should be satisfied and what properties have not listed. So unlike a factor graph where all the variables were connected to all the functions that they participated in, here that's not the case. Right? It should be a tree, and you look at the subgraph of which involves only xi, this should be connected. That is it. I'm not demanding anything. Sorry? No. Because then it would be impossible to construct it. Right? If one variable participates in at least 3 functions, then that will be a triangle. It has to be fully connected, means that it will have a cycle. So this is one particular junction tree. But if you look at this example, we sort of seem to do it in an ad hoc fashion. Right? Is it possible to systematically get this? It's not straightforward. I just brought it up. The question is there a systematic way to construct a junction tree? Or find out whether it's possible to construct a junction tree. So in this particular example, there are two things, right? So we had an original, we tried to construct a junction tree in kind of a greedy fashion, but we saw that it's not possible to. For this, if you had only these 4 local functions, then it's impossible to construct a junction tree, as we tried to. But on the other hand, I somehow just introduced these 2 new local functions. And for this, again, it was not, even if I gave you these 6 local functions, it was not entirely straightforward to construct this junction tree. So, and this involves 4 variables. It is so complicated for this, then if I give you an even bigger function, then it will be even hard. So can we construct a junction tree in a more systematic? It turns out that it is possible to do. And the way you do this is using the following approach. So once again, you're given alpha 1 of xs1 times alpha 2 of 2 to m of xs. So for this, I want to construct a junction tree. Right? So you first start. So here's an algorithm. So the first step is to construct what I call the local domain graph. LD graph. I'll call it GLD. So this is a complete graph. On the M vertices. Alpha M. But this is going to be a weighted graph. So each edge is going to have a weight. Each edge I comma j as weight wij, and this is equal to the size of the intersection between Si and Sj. The first step is to construct this particular local domain graph. The second step is you find a maximum weight spanning tree the local domain graph. There are different algorithms to compute the maximum weight spanning tree, and you use one of those algorithms to find it. Okay, a spanning tree. So what is a maximum weight spanning tree? So a spanning tree is any tree which contains all the vertices. So a tree means that it is connected, of course. Tree that connects all vertices. GLD. So there are multiple spanning trees for this given graph. For each spanning tree, so a spanning tree only has a certain number of edges, right? You basically get it by throwing away some of the unnecessary. Now, the weight of the spanning tree is the sum of the weights on the edges which remain in that particular tree, and you choose that spanning tree which maximizes the weight. So the weight of the spanning tree is basically equal to some weights edges. So for example, if I give you the following graph with so one particular spanning tree is this, right? What would be the weight? 1, 2, 1. So the weight of this particular spanning tree is 2 plus 1 plus 1. Here is another spanning tree. this has weight equal to 1 equal to. But is this the only maximum weight spanning tree? So what if I take so this is also a tree, it's a spanning tree, and it has the same weight as this. Right? So for a given graph, particularly for a given complete graph, there's a notion of maximum weight spanning tree, but it's not unique. There can be multiple spanning trees which give you the max. So the second step, you first construct this local domain graph given your local functions, and you compute the maximum. You find the maximum weight. We find one maximum weight spanning tree. Third step is find the maximum weight. So let me call TLD. Let me call this T. So if the weight of the maximum weight spanning tree, if it is equal to the following quantity, W star, which I will define as summation I equal to M size of Si minus N. So this is what I call my target weight. So if the weight of the maximum weight spanning tree is equal to this target weight, then this will be the tree that I get. The maximum weight spanning tree will be a junction tree. E is a junction tree. If it is not, then it turns out that it's impossible to construct a junction tree for those particular local functions. And the only way you will be able to construct a junction tree is by adding more local functions. Yeah, you'll have to add some more local functions, some dummy local functions, and then you might be able to construct a junction tree. There is an algorithm for well, but I don't want to get into the details of that. Again, even that approach, it is not unique. There are different ways to construct, and that turns out to be more of an art than a systematic approach. Which the one adding extra can be done, but it's a little more, slightly more art. Yes. So you'll have to look at all possible cycles and make sure that every cycle of length greater than 3 has to be sort of chordal. That is, there should be an edge between those two. Yeah, again, you can make it systematic, but then other considerations creep up, because the way you add these extra local functions strongly determine the complexity of your ultimate algorithm. Again, so far we've not talked about algorithms or anything, we're just constructing junction tree. So if your goal is to just construct a junction tree, then yes, you can do it in systematic fashion. But so far, there is more or less a unique way to do it. So given a set of local functions, you know, okay, there are multiple maximum weight spanning trees, but then it turns out that these don't influence anything. But now that you have, if it is not possible to, then you'll have to add more local functions. And there, depending on how you add the local functions, the complexity of your algorithm will ultimately be. There are different ways of adding. So I've given you a procedure, but now really I'm not, we don't know whether it is always going to be a junction tree or not. For that we need a proof, right? So it turns out that the weight of any maximum weight spanning tree is always less than or equal to W star with quality if and only if T is a junction tree. So if it is strictly less than W star, then it's impossible to construct a junction. Okay. So firstly, you should convince yourself that any junction tree has to be a spanning tree of TLD. It has to be some spanning tree. It is always a spanning tree because after all, it has to connect all the vertices and it has to be a tree. So by definition, it is a spanning tree. So we construct that spanning tree. Again, we're going to construct it as a maximum weight spanning. So in particular, if the weight is less than this, then it is impossible to construct. So we'll see how to connect the weight of the tree with the condition of whether it's a junction tree or not. Okay. So now remember that we have m local functions and n variables. So we'll do a little bit of double counting. So let us look at. I will define mk, m subscript k, as the number of local functions that the kth variable participates in. So for example, in our toy example, x, y of yz, m1 is equal to just 1 because x participates only in f. m2 is 2 because y participates in f and g. And m3 is equal to 1 because z participates only in g. So that's what I mean by mk. Now, what can we say about summation k equal to 1 to n of mk? Okay, so in relationship with this, with the following quantity, summation I equal to n summation size of S. Yeah, less. Okay. Can you say something? Okay, I agree that it will be less than or equal to. Can you make a stronger statement? Is it true that it's always equal? Yeah. In the toy example, it is. Why? Okay. 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 Correct. So what does MK correspond to? Okay. Correct. Still doing it in 2D. So I mean, another way of thinking about it is using the factor graph. It's essentially the same as you said. So you draw this factor graph. What does MK correspond to? Is basically the number of functions that the kth variable participates in, right? Or in other words, it is this sum. It is the total number of edges going outside, going from each variable. So what does summation MK give you? The sum of all the edges, which is the total number of edges. Correct. What does size of Si correspond to? It is the number of variables which participate in that particular function. So it is the number of edges incident on one particular function. The summation of these gives you again the total number of edges. So here what you're doing is basically counting the total number of edges in the factor graph. And both have to be the same. Right? Okay. So now let us consider the maximum weight spanning tree. Right? Or in fact any particular tree, right? Any particular spanning tree. So let me define something. So WK is the sum of edges sum of edges, or the number of edges in T that contain xk. So corresponding to each edge here. So again, you look at the local domain graph. Let us take this particular example. So this would be the local domain graph. So each edge essentially corresponds to a bunch of variables, right? And those are the variables which are common to both functions. So this particular edge corresponds to x2, this edge corresponds to xp, this edge corresponds to x1, this edge corresponds to 4, this edge corresponds to empty, and this edge again is empty, right? So if I consider any spanning tree of this, I look at the number of edges in that spanning tree which involve that particular variable. What can I say about this? So if I compare it with MK, so MK, so I look at this complete graph, right? And once again, I can think of MK in also the following way. I look at this complete graph. I have the edges being labeled by the variables which are common to both, right? Now, if I look at the total number of edges involving, say, x1 or x2 or x3, what is it equal to? By mk by 2? Yes, correct. Okay, correct. So k is equal to 2. But is it mk by 2? Yeah. Mk minus, correct. So now if it were a spanning tree, so what can you say? Is it going to be less than m? Do you agree that it's always going to be less than or equal to m? In fact, it's going to be slightly less, even lower than mk. It is going to be at most mk minus 1. If it is a spanning tree. So you take the spanning tree, you take the subgraph of the spanning tree which involves only x1. What is the total number of vertices? Yes, but in general, no. The number of, so it's the total number of local functions which involve xk, which is exactly equal to mk, correct? How many edges can this have in the spanning tree? Mk minus 1. If it is fully connected, then it should be exactly equal to mk minus 1. If it is not connected, if it contains not if the subgraph is not connected, then it could be less than mk minus 1. Right? So if I look at wk, this is going to be always less than or equal to mk minus 1. And it's equal to mk minus 1 only if that subgraph of the spanning tree is fully connected. Right? Okay, so now let me sum. So what is the total weight of the tree, spanning tree? It is the sum of all the weights. So it's summation k equal to 1 to, and the sum of the weights is basically equal to the summation of w. You agree? K equal to n wk, but this is, as we know, is less than or equal to summation k equal to n of mk minus 1, which is summation k equal to k minus n, and this is equal only if all the subgraphs are connected. In other words, if it's a junction tree. But as we just saw, summation mk is summation which is w star. Right? So this is a systematic way to find out whether a junction tree exists. If a junction tree exists, then this gives you the junction. So again, let us try to apply this to all our cases. So in the first case, so that's example 1. That's fairly trivial. You have f of xy, of yz. There are only two functions. It's connected. It's already a tree. So there's nothing more to do. This is already a junction. Let's take the second example. So there I had alpha 1 of x1, x2, alpha 2 of x2, 3, 4, x1, x4. So let's construct the local domain graph. 1, 2, 3, 4. What are the edge weights? Okay, what is W star equal? So it's 2 plus 2 plus 2 plus 2 minus 4. So 8 minus 4, which is okay. Now consider any spanning tree of this particular graph. Right? What is the maximum weight that you can get? You don't have any spanning tree with 4. Maximum weight that you can get is 3. Because any spanning tree can have at most 3 edges, and since the weight of each edge is less than or equal to 1, maximum weight you can get is. So in this case, the weight of any spanning tree strictly less than 4, therefore no junction. So now let us look at the other. So this. what are the edge? What is W? 14 minus 2 plus 3, 4. There are 4 variables. Now, is there a spanning tree as weight equal to 10? Let's say I keep only those edges a weight 2. Okay, remove. The maximum weight spanning tree. What is the total weight? 10. And this is a junction tree, exactly the junction tree that we had previously. Of course, we are trying to do it by hand, so finding the maximum weight spanning tree seems a bit complicated, but there are algorithms which let you do it automatically. And any maximum weight spanning tree is going to be a junction. So that is it. So now, given a particular local function or a set of local functions, we know how to construct a junction tree. Now the question is, how do we solve the MPF problem? Right now, we're only trying to get graphical representation. Okay. So this algorithm and the general algorithm that we'll use to decode LDPC codes are going to be are specific instances of what are called message passing algorithms. So that they fundamentally depend on the graph, and you can think of this, so it's an iterative algorithm wherein along each edge you pass sort of a message, and you run this iteratively till eventually some stopping point is reached, and at the stopping point you get the final answer that you're looking for. So let's see this with one particular example, the toy example that we have. F of xy, g of yz. We have an edge between these two. The goal now, let's say, is to compute summation overall x z f of y g of yz. Okay. So let us think of the following algorithm. Okay. So now this vertex over here, it knows g of yz. This vertex knows f of xy. But this vertex doesn't know anything about g. This vertex does not know anything about f. So each of these vertices, they only have this local information. They don't know the information of the other local function. all they can do is convey the information about their local function to the other vertices, right? But then we don't want to convey more than what is necessary. One way to do it is you send the entire g of yz to this particular x. So this will be a vector containing g of yz for all possible y and z. You send it to this particular vertex, and this vertex again multiplies with it knows f of xy. Basically, it maintains a table of or a vector of f of xy for all possible xy pairs. You can multiply the two together and compute. Okay? But now you don't have to send all of this information, because now this is a function of x and y. It's not a function of z. So what this vertex can do is first marginalize with respect to z and send a vector of all the information corresponding only to y. Because this vertex, all it needs is information corresponding to x and y. It does not require information corresponding to z. So this vertex will send a message. I'll call this 1 and 2. So this is vertex 1 and vertex 2, corresponding to alpha 1 and alpha 2. Yep. Which one? Again, the goal is to compute this sum of products. That's it. That's all, right? Yeah. Again, you don't, what I'm trying to argue is that you don't need information corresponding to z individually. You can sort of marginalize it out. So let's think of the following algorithm where this sends a message mu from 2 to 1. So I'll use this particular notation. So it's a message being sent from alpha 2 or the second vertex to the first vertex. And this message is going to be a vector. Actually, all of these messages are going to be vectors. And the vectors are going to be indexed by the variables which are common to both. So remember that each edge could be labeled by the variable which is common to both functions. In this case, it is y. Y is common to both functions. So this is going to be a message which is going to be a function of y, or it's a vector of some vector indexed by y. Okay. And what is this message going to be? Okay. This is going to be summation of whatever it has, p of z, some overall possible. Okay. Let's say that we get this. Now, what is this variable going to do? It is going to take all the messages that it has received. Basically, it just gets one message, which is a vector. It multiplies with its local function and then takes a summation. So I'll call it beta hat. So this is going to be a summation over all possible x and y. So it has information only about x and y. Its local function times the message it has received. 1 of y. But what is this equal to? This is summation over all y, f of xy, summation over all z, g of yz. But this is exactly equal to, just that we decided to sum with respect to z first. And in doing so, we basically use the distributive law. Exactly the distributive. Right? Okay. So right now, let us look at the total number of computations that we perform. So again, brute force, this requires size of x times size of y times size of z. Right? That's the total computation. Now let us see. So first, this particular algorithm, what did it involve? You first had to compute the messages. What is the total complexity required over here? You need to find that for each y. right? So total complexity is size of y times size of z. So this is the total complexity to compute this message. Now once you get the message, you have to do some more computation, right? So this requires one multiplication and a certain number of addition. Or in other words, the total complexity of this is order size of x times size of y. Agree? So the total complexity is size of y times size of z plus order size of x times size of y. Correct? So the complexity of each local function, locally the complexity just is determined only by the number of variables it has, right? And that is what is happening in each step. So the complexity is determined by the maximum, in some sense, the maximum number of variables in each local function and the total number of edges, because for each edge you have to compute a message, right? And that is it. So right now, just by doing this, we reduce the complexity from size of x times size of y times size of z to just this. Right? So the next class, we'll analyze this in a little more detail. We'll see junction trees for each of the examples that we dealt with previously, and also try to find the complexity of try to get a bound on the complexity of solving it using this particular procedure. Correct. Yes. So if you have local functions which involve a very large number of variables, then you're not really solving anything, right? The complexity is still determined by the number of variables that are involved in the local function. So if there's one local function which involves too many local variables, then you don't get any real reduction in complexity. Then if I have a larger number of local functions, each involving a very small number of variables, that's beneficial to me, because the complexities kind of add up, they don't multiply. So let's stop here.